Okay, let's get started today. Today we're starting to dig into some of the real heart of kind of networking. And before too long, in the next couple classes, we're actually going to be writing code that works over the internet. So today, though, before we dig into that, though, it's helpful to have an idea of why the framework of the internet is set up the way that it is. And so today we're going to talk quickly about the OSI model. And essentially, the idea behind the OSI model is that if we look at what we have talked about previously, we talked about this concept of both packets and protocols and the way those interrelate to one another. So the first off, if you think about a packet, packets are essentially like this block of data. And that data itself has kind of a header that gives us information about that data. It might be a sequence number, might be a version of the protocol, it could be other things about it. And then it has the actual data part itself. The payload is usually what that's called. But there's also usually some sort of check value associated with the data as well. So in other words, we have this block of data that we can verify whether it's correct or not, and we have some other information, some sort of meta information about the data. Where does it go in the sequence? Is it the first packet? Is it the last one? Things like that. Now, the protocol is a set of rules for how we deal with those packets, or what do we do about that? So if we get a packet with a bad check value, what do we do about that? If we get a value in a sequence number in the header that says it's out of sequence, and that means we lost a packet, what do we do about that? So the set of rules becomes important there. And the last time we ended up the discussion of that by talking about some real-world protocols, and we mentioned how they can be kind of used together or layered together. And so the idea here is of layering those packets or kind of using them together would be something like a traditional web page when you go to visit it. So you go to a web page on the internet, you go to your favorite news site, or you go to Reddit, or you go to, some sort of site that has memes, YouTube. Those things are using multiple packets and multiple protocols together. So for example, HTTP is at least the non-secure version of the hypertext transfer protocol, kind of the language of transmitting web pages from one place to another. HTTPS is the same thing, but adds a little bit of security to that. And then those use that, both HTTP and HTTPS use TCPIP to communicate. So they're sending their data over TCPIP, and TCPIP is actually a suite of protocols that use kind of a lower level network protocol, such as Ethernet or wireless Ethernet, Wi-Fi, and those use this other protocol. And then Ethernet is this low-level protocol that's actually putting the data onto the wire or putting it into packets that are sent over wireless from your laptop to an access point. But the idea there is that those are all working together. Now, what we're going to talk about today in this OSI model is like how is it organized that those work together. For example, you can't put an HTTP packet directly onto Ethernet. You also can't have HTTP exist without TCPIP and without Ethernet at the low level. And so why are they layered? How do they work together? How is it organized that it works that way? Now, so one thing to note is that each of those protocols we talked about kind of has a different set of rules and a completely different structure to them. So the idea there is HTTP messages, the way that the contents of a web page get transmitted to a web browser and then displayed, it has to go over TCP/IP to some web server, has to get the data, and then that data has to then be rendered into the screen on your machine in your web browser. And then in order for that to work, TCP/IP has to be able to send packets to your router over some sort of methodology that's not really TCP/IP at that point. But then notice that could be different. It could be a wired Ethernet. It could be Wi-Fi of some sort. It could go over for example, a combination of those. It could go Wi-Fi to your access point and then wired to your router, and then from there it could go over fiber. So there's these different low-level protocols that are happening. So the question is, how can those work together cooperatively? And in order for them to work together, we have to have kind of a overall organizational structure that allows this kind of cooperative behavior. And the answer to how do we set something up that will allow this cooperative behavior, especially considering that some parts of the lower level, for example, might need to be taken off of wireless, put onto a wire, taken off of a wire, put onto fiber in an optical form. And so the answer to how to do that and do that in a way that is kind of manageable is to use this layered model. And what the OSI model is, it's kind of a standardized approach to creating a layered set of protocols for networking. All right, so what OSI stands for is kind of Open Systems Interconnection. And that's a part of the ISO, the International Standards Organization, came up with this kind of, here's a standard model for doing kind of this layered protocol, layered communication. So first, let's take a quick look at a bit of history here. So until the OSI model, and until it kind of became adopted as kind of this standardized way that you should organize networks, most computer networks were these proprietary things that came from large companies like IBM or Digital Equipment Corporation, and they were implemented in like vastly different manners, which made them incompatible with one another. In other words, if you had an IBM network and you had a Digital Equipment Corporation, a DEC network, the devices couldn't talk to each other because they were completely proprietary. And that difficulty in getting diverse types of networks, different brands, manufacturers, equipment to talk to each other started to become a problem once computer systems started getting more networked with each other. And so what happened was the ISO, International Standards Organization, they set out to define this kind of method or a model that would make it easier to interconnect kind of different kinds of networks as long as they kind of followed this standard. And the idea there was that you wanted to have it so you could take your IBM machine, stick it on a network with Data General machines or any of those other large companies, DEC, Hewlett-Packard, whoever else was making computers at the time. And we want to be able to stick them together and have them talk to each other, because if you're going to have a network, it doesn't do any good if the machines can't talk to each other. So they came up with this kind of model. And so it's really, the ISO model isn't really itself a standard for protocols or a protocol itself. It's kind of a conceptual way of organizing things that make it much easier to then connect them together. All right, so that is where the OSI model came from. And the idea there, this Open Systems Interconnection model, had two major components to it. The first is kind of this abstract model of networking, which is what we're going to look at today. It's kind of the basic reference model, or sometimes called the 7-layer model, or just the OSI model. But the idea there is that it itself is not a protocol. It's more of a way to create protocols that will allow them to more easily be interconnected to each other. It also included a concrete set of protocols that followed that OSI model. And as we'll see next class when we get into TCPIP, it kind of loosely follows the OSI model, but some of the parts of TCPIP kind of encompass multiple sections. So it does follow the hierarchy of the OSI model, but you can't look at TCPIP and say this part of it exactly fits this part of the OSI model. It's a little more coarse-grained than that when we get to TCPIP. All right, so let's take a quick look at what the OSI model, kind of that kind of basic model, is set up as. And essentially the way it's set up is it has the networking system. So if you think of, here's some data, I want to get this to another computer somewhere, it divided the functionality of that up into these different layers. And what we mean by different layers is essentially the idea is that each layer, it's up to kind of one or possibly more entities to implement that functionality. So in other words, we're kind of stratifying the functionality into different types of behavior. So the idea is that each of those layers will interact only with the layer beneath itself and then provide a set of functionality, or you can think of it kind of like an API for use by the layer above it. So we'll come back to that here in a second. So the idea is that protocols, in that case, the idea is that we want to have the local host interact with, let's say, at the application on your end. So you have these two programs and they want to communicate. Well, they don't really necessarily care about how all the networking stuff works. They just say, I want to send data from this web server here to this web browser over here. So you want the data that's on the web page that's being served to somehow go out over the network and then show up on the other end. And so web server, here's here's the web page, web browser gets it, renders it on the screen. So notice in that particular model, the idea is that the entity on one machine, one host, is going to interact with the same level on the other end. In other words, web browser goes to web server. But then if we go down a layer and think about HTTP, the HTTP encoding that web page is going to act to the HTTP decoder on the web browser. And the TCP part, which we'll see later on, is dividing it up into the individual packet stream, taking a large amount of data, to segmenting it, dividing it up, giving sequence numbers. That's going to interact with the entity on the other side. It's the TCP layer. The IP layer that's doing the routing, that's going to interact with IP layers of devices as they go across. And then the Ethernet or Wi-Fi on your machine is going to interact with the thing. So in other words, think about all these layers as kind of being kind of connected and only really interacting with providing services for the layers above, using the layers below to accomplish tasks, and then interacting with the layer across on the other end with the machine that it's talking to. So that allows for this very kind of modular architecture. And that modular nature of that is what allows us to have these kind of dissimilar networks still work together. All right, so let's dig in and look at the model a little bit more carefully. All right, so we said there were 7 layers. And if we look at what those 7 layers consist of, we've got essentially, I've kind of divided those up into 2 kind of groups here. What I'm going to call host layers, and then down here what we're going to call media layers. But the idea is that let's just start at the top here. So at the top, layer 7 is the application layer. And so that's kind of the application using network features, doing things on the network. And again, that would be, in our case, web server sending data to the web browser. The next layer down is the presentation layer. And what the presentation layer deals with is kind of encoding the data and decoding the data. So that how is the data represented? Is it encrypted or not? So if you think about something like HTTPS, the secure socket version of HTTP, so encrypting the data for the web page and the server, sending it, and then decrypting it on the browser, that would be something that we could think of as being at the presentation layer. In other words, that's not something that the web browser itself cares about. It just still cares about getting the data to render the web page, but getting that from the server. But if we're going to encrypt that so nobody can see what's being looked at if they were to snoop the packets that are traveling the network, then encrypting it makes a lot of sense. So we just add this kind of encryption layer in here. The next layer down is the session layer. That deals with kind of starting a session, ending a session, saying I'm connecting, okay, you're connected, and then at the end saying, okay, I'm done sending, okay, close down. That's stuff that would be in the session layer. In other words, starting the communication, canceling it partway through, finishing it up when we're done. Now, below that, we have this transport layer, and the transport layer is part of saying, okay, here's a lot of data. We need to segment that into different datagrams or different packets, and then we need to send those to the other end. We need to make sure that all of the parts were received in the right order and reliably. If parts were missing, then we need to re-request them. So the transport layer is responsible for getting a large amount of data dividing it up into these individual packets, and then sending them across the network to the other end. Now, the network layer is below that. That's the thing that adds logical addressing to the packet. So you can say, okay, this packet is intended to go to this machine from this machine. It also is the part of the packet that's used for routing. So when I say, hey, connect to google.com, google.com has an IP address associated with it that gets put into that packet, and we drop it onto the network, and then that kind of packet goes around and uses this the logical addressing to determine where it gets routed to next. The data link layer, which is below that, is more of the physical addressing to say, okay, I know that the logical address says I need to go. That's not in my local network. It needs to go to the router. So it goes to the router. The router then looks, or we put the physical address of the router in that packet. The router reads the packet and says, okay, that's not for anyone in this site. It's somewhere else. So it routes it to another, the next router upstream from it. But notice that this is changing. The MAC address of who it talks to next is changing. But the logical address up here is going to stay the same. So when I talk to a website like google.com or in my company's case, yoastlabs.com, that has a physical or a logical address associated with it. But the physical address of that server is kind of irrelevant because the routers are going to handle talking to the next one up the chain. Now, at the lowest level, level 1 is considered the physical layer. That's the actual media or wireless signal that's actually doing the binary encoding and decoding of that. So that could be bits or bytes traveling over a wire. It could be bits or bytes that are encoded in some way traveling across whatever the channel is. So the channel might be Wi-Fi, it might be optics, it might be, like in the case of fiber, it could be electrons in the form of something encoded on a physical wire, but that's the physical layer. Now, there are a couple other layers that you'll hear used sometimes, terminology. Layer 0 kind of jokingly refers to the physics of the electrons, or sometimes layer 0. If somebody says that their server experienced a layer 0 problem, that means that it was nowhere in any of this. It was actually, sometimes I'll use that to mean there was a power outage. So I had a layer 0 problem. That would mean there was some sort of power outage, or the wire itself got cut. Something like that would be layer 0. And then on the other end of that, above the application layer, you'll hear some jokingly layer 8 referenced as an end user problem. So if there's nothing wrong with the application or the network or the communication or anything, everything's working as expected, but there's some user having a problem. We'll say, oh, we figured out the problem with the system was a layer 8 problem. And notice that means really no problem in any of this. It's a problem with the person using it wrong or not understanding what it was that they were using. All right, so those are the 7 layers of the OSI model. And you'll notice that there's also this data unit segment here that we're talking about, the kind of stream of data. But then once we're down to the transport layer, it's segmenting the data into individual kind of datagrams. Those are then being put together into kind of these individual, it says packets here, but I'd maybe refer to this as datagrams as well. And then down here, frames of data that are actually Ethernet. You can think of that as packets if you want to. It's kind of a block. These are all kind of blocks of data from here down. But the difference between the blocks from transport and network and data link is that they're kind of wrapped inside of the packet from the one above. So in other words, we have some HTTP data that makes a web page. We divide that up into TCP segments that have their own header associated with them. And then we take those and wrap those in a network kind of packet, an IP packet that has not only does it have the data part of the data we want to send in the TCP header that has the sequencing stuff, but then on the front of that, we are adding the addressing onto that. And then that goes onto the physical network, or has to go onto the Ethernet network. So on that, we're going to add another header and a check value at the end of that. That's going to actually be the Ethernet packet that actually goes out across the physical wires down here. All right. Now, let's go through these layers kind of one at a time and get a little more detail in them. And to give a little more detail, the physical layer, we're going to start from the bottom and work our way up rather than work our way down like we did in that chart. The physical layer essentially defines electrical physical specifications for devices. So if you have something like an Ethernet cord where something plugs in, that would be the pin layout, what voltages are on that, what are the cable specifications. So that would be things like Ethernet, like Cat5 cable with a RJ45 end, and these are the pins, and these are the voltages, and here's how the signaling works on that. So that's kind of this low-level physical specification for some signal. If it's Wi-Fi, it's like, okay, this is the frequency band it's in. These are the kind of ways that the data is modulated on that frequency band. These, if it's like a spread spectrum system where it jumps around, here's how it jumps around to different things. Here's any kind of forward error correction that happens on there. All of that is part of that physical specification. So things that exist on networks that are in that are things like hubs or repeaters or the network adapter for your PC when you plug it in, or the Wi-Fi adapter. Those are all physical layer devices. Now, the physical layer does overlap some with the data link layer that we'll see here above it, but we'll look at that. Now, what are the jobs of the kind of physical layer? What service does it provide to the layer above? Well, in this case, this kind of establishes and terminates connections to some media. In other words, if it's acting as the gateway to the wire, it has to say, okay, now I'm going to put stuff on the wire, and then I'm going to stop putting stuff on the wire. Also, notice there, the other thing that might have to do is come up with a way to a process to share that resource. So in other words, if you have, for example, Wi-Fi, there are a lot of devices that might want to be talking over the wireless at any given time. So there has to have a way. What happens if they both try to talk at the same time? What happens if I'm sending data faster than the machine on the other end can receive it? So there's kind of that contention resolution. Contention is just where two things try to talk at the same time or try to use the network resource at the same time. And then flow control is sending data too quickly and being told to hold on a second. And that can be part of the physical layer devices as well. Now, also the actually putting the data on there, modulation to put the data on the channel. And the idea there is that somehow we have to take this digital representation of data, meaning the binary ones and zeros that make up the content of the message, and we have to put that as a signal over the wire. And we previously in the class, we've looked at a lot of ways to do that, including things like self-clocking codes like Manchester encoding. And it turns out that Ethernet does, the wired form of Ethernet does something like that. It has Manchester encoding as part of the way it works. So essentially that's the signals being put onto some physical media, whether it's a copper wire or a fiber optic cable or a radio frequency at a certain with a certain modulation methodology, or it could even be light of some sort for a infrared communication. It could be near field communication with a smartphone. But in other words, the physical layer deals with the actual physics of that and how that thing gets modulated. All right, so to finish up the physical layer here, there are a whole lot of standards that operate in that. A few of them I put here: physical layer Ethernet. And although, if you remember, I had mentioned that part of Ethernet is in the data link layer as well. But there are other examples of this as well. RS-232, a thing called SCSI, which used to be a way to connect computer peripherals together. You don't see much SCSI stuff anymore. Token ring hardware, FDDI, which is a fiber data distributed interface. That's a fiber optic thing. 802.11, which is wireless. It has a bunch of variants of that. So that's Wi-Fi, Bluetooth, Zigbee. And there are a whole lot of other, LoRa, there are a whole lot of other kind of physical layer kind of standards that are in that space. All right, so now let's move up to the data link layer. And the data link layer, the idea of that is it provides kind of this means to take the data. What service does it provide? It takes some sort of data, puts it into an actual packet that then gets put on the wire. So the idea here, it makes it possible to transfer data from one network entity to another and then detect if errors happened in that transfer. So possibly correct too. A lot of wireless systems use like a forward error correction in them, which we've talked about previously. And then the other thing is that at this level, the network entities have to have some sort of physical address associated with them. So Ethernet, for example, every device has this unique physical hardware address, they call it, or the MAC address. But those addresses are kind of included in that packet that gets created. And notice there I said the best known example of that is Ethernet, which is both a physical specification for how things get connected and what kinds of connectors and what sorts of wiring characteristics there are associated with it. And it also has the data link specifications for not only is this a physical specification for like the port that you plug into with the pins and the voltages, but it also says, and then here's how you make packets that go on that specification. And Ethernet has a number of different variants. There's 10 base T, 10 base 2, 10 base 100, and then all of the Wi-Fi are kind of extent variants that are 802.11 are all variants of wireless Ethernet of some form or another. But kind of that data link layer, the idea there is that for Ethernet, that can be split into a kind of the MAC layer, the media access control, and then the logical link layer, which is kind of the layer that's actually creating the packets. So the media access control is kind of the low level where we're adding the physical addressing and putting it out there. The other level above that is kind of the logical link control, saying here's some data. How do I put that into Ethernet frames to be sent? And notice that I say that in the next sentence there. It says bits from physical layer organized into logical chunks of data known as frames. So in other words, that when we're sending stuff across that wire, we're organizing it into these packets or frames. And that's the layer at which bridges and switches operate. So if you have a network switch or a network bridge that connects two networks together, then those are looking at the kind of hardware MAC addressing of the packets and deciding which port of the hub their data gets routed to, or which things go across the bridge and which ones don't. And notice that kind of the MAC addresses, the hardware addresses, are associated with Ethernet devices. In next class, we're going to dig into the specifics of that. But right now, just know that every Ethernet frame that goes across there kind of has this hardware addresses as part of it. And those are kind of uniquely created at a factory. So if you buy a device, like for example, here's a kind of a phone, conference room phone system, and notice that it has kind of these Ethernet ports on here. This actually has a hardware MAC address associated with it, and if you look at the back of the device, there's a little barcode here that actually says what the hardware address is. So every one of these devices that gets created has this unique address, and that's what's used at the Ethernet level to talk to those, and that's hard-coded on those devices. All right, moving the next layer up, the network layer. The network layer is essentially responsible for transferring not directly from one piece of hardware to another piece of hardware over the wire, but this is the network layers deals with how do I get something across an entire network. So in other words, you've got this network that might have 10 different connections or hops that it has to go through. Well, we can't really keep track of each of the addresses of those, so that's why we want to use something like a logical addressing, like an IP address. So when I talk to something like the university's computer system, and it's on a particular IP address, that IP address isn't the hardware address of that, it's kind of the logical address of it. So the idea is what the network layer does is it routes packets kind of from source to destination, maybe going through multiple networks. It could be a direct connection, but it could also go across a lot of different networks. So the network layer performs logical addressing, network routing function, and it might also need to perform segmentation, desegmentation for certain data link service types. In other words, if there's a data service type that the packet that we have, the datagram we have, is too large, it needs to be cut down into smaller subframes and then put back together again. And the network layer could be partially responsible for parts of that. All right, so routers operate in that layer. We had mentioned that. And IP is a good example of a protocol that's at the network layer. And one of the ways to visualize that is kind of the postal mail system with mail carriers that move letters from point A to point B. that the letter has an address of not what mail station it goes to next, but what eventual destination it goes to next. And so the mail system will look at those letters and say, oh, this is a letter that needs to go to this sorting station, so we're going to send it there. But the thing they're using to determine where to send it is the logical address that's on the outside, the destination address. All right, the transport layer essentially provides this kind of method of transferring data from one user to another user in kind of a seamless way. So the idea there is the main idea behind the transport layer, you can think of it as it's responsible for segmentation and desegmentation, and then making sure that reliability is enforced. So in other words, if we have a really large amount of data, too big to fit in any one of those little segments that we're going to send, then we need to cut that up into smaller pieces and then put it back together on the other end. And if pieces are missing, we need to fill in the blanks. That's the whole idea of the transport layer, is kind of the segmenting and sequencing and then verifying reliability. If we say something was sent, we want to make sure that it really was sent and received on the other end. Notice here, I have a thing that says some protocols are state and connection oriented. And that means that the transport layer might need to keep track of the sequence and retransmit those that fail. So in other words, I might have to, once a connection has been opened, I may need to keep track of what state I'm in. I can't just throw all the packets out there and say it's good. I'll need to put them all out there, wait for them to be verified. If any were missing, I would need to resend those, but only the ones that failed. All right, so the best known example of that layer 4 is TCP, the Transmission Control Protocol for TCPIP. And now you can start to see how TCPIP has these multiple layers inside of itself. It's got TCP and then IP. And TCP is responsible for segmenting the data into individual datagrams, and then IP is responsible for putting addresses on those datagrams. So you can think of it as the idea there is pretty straightforward. Imagine you have this large book that you need to send, and all you have is envelopes. Well, you might divide up the book into smaller amounts of pages, stick them all in their own envelope, and then put a number on the envelope. So the dividing up and putting the numbers on the envelopes would be TCP's job. And then IP, the lower layer that we already looked at, its job would be to put the address on there and make sure that to route each of the things. So the postal system doesn't care about the numbers on the letter. All they care about is the end address. It's the person on the other end who has to put it back together into a book that's going to look at the numbers on the letters. And then if any are missing, they'll have to write a letter back saying, hey, I missed pages or letter number 46 and 105, resend those ones. And you can kind of see how that's different responsibilities for each of those segments or each of those layers. All right, layer 5 is the session layer. And the session layer is responsible for kind of setting up the conversation, saying, hey, I want to connect to you. The other one saying, okay, we're connected. And then at the end, one of them saying, okay, I'm done. And then the other one saying, okay, cool, let's close the connection and shutting down. So think of that kind of like, if you think about this sort of like a conversation, you walk up or you want to ask somebody a question, you'll get their attention. They'll say, okay, go and ask your question. You ask the question, they give an answer, and then at the end you say, okay, you done? Yes. So think of it kind of like an extended conversation. And notice that this is a little bit different than the segmenting, although this is done in TCP as well, in TCP/IP. Remember how we said TCP/IP has kind of crosses multiple layers with parts of it. But the idea here is the session layer is responsible for establishing a conversation or a connection, managing it, and then when we're done, terminating it. And that's between the two ends that need to talk to each other, the two entities that need to talk. So the idea there is that this thing is kind of starting the conversation, making sure it continues, and then adjournment here means closing it down, or termination if we're partway done and say, never mind, I want to stop right now. Or maybe even restarting it, saying, let's try that again, because something went wrong there. So the OSI model made that responsible for kind of opening sessions, gracefully closing sessions, And that is done in TCP. So TCP has both kind of session layer and transport layer parts that it does. All right, layer 6, the presentation layer. We mentioned this earlier, but that's primarily responsible for kind of encoding and decoding data in some way that might be important for the application layer above. So that could be things like endianness between different architectures. So this architecture is a big endian, this other one is little endian, somewhere that has to be switched or the data is not going to make any sense. And that's usually the part of the presentation layer. Compression, you have something where you have a stream that you want to compress and send, and also encryption, like we mentioned SSL or HTTPS. Presentation layer would be that. It's not really something that the application itself is doing. It's something we're saying, hey, here's some data. I want you to encrypt it for me, send it to the other end where it'll be decrypted. So anything that's manipulating the data stream in some way could be considered presentation layer. So in other words, that layer's job is to convert to and from the format needed for the application layer itself. And then finally, the application layer, that's providing kind of a means for the application to access the network and send information through it. And notice that most applications, they don't care about all the stuff that's going on below them. They just say, here's some data. I want you to write that to the machine on the other end. And on the other end, they say, okay, I'm connected. I want to read that data. So the application layer is going to make calls. When we get into the programming part of this, what you're going to see is the application layer portion of this is going to be making calls to kind of the lower level things to open the connection, to send data, to close the connection. And it's just going to use those kind of lower levels as a tool. And it doesn't really care what the packets look like or what's going on down below. It just says, hey, contact, just like when you make a phone call to someone on your smartphone. So you take out your smartphone, you power it up. You don't really care about how the signals get from this to the thing. Is it 5G? Is it 4G? You probably don't really care. If you just want to call somebody and talk to them, all that matters to you is that those layers work correctly. So at the application layer, and again, this is why this is a layered model, is that the application says open a network connection to this address. Once it's open, send this data, send some more data. Once I'm done, close the connection. We just want it to work right below there. And that's why we rely on those lower level layers. Now, at the application layer, however, you can still have a protocol. For example, notice there's a protocol think about making a phone call as the application layer for a smartphone. And so there's a protocol for making a phone call. You dial the number, you wait while it rings. Once the other person says hello, then you can start talking and say hello back. And when you're done, there's a protocol for concluding the call. You say, okay, I don't have anything else right now. I'll talk to you later. Bye. They say bye, and then you hang up. And so there's a protocol for the higher level, what you do with the data that goes across there. That has to be agreed upon as well. So at the application layer, you might have we talked about a web browser, web server application. That would be something like HTTP or HTTPS. That's a protocol that sits kind of up in that application layer area, or email with SMTP or POP servers, or file transfer, FTP. There are a whole bunch of different things. Or it might be a game server where we create our own protocol for how to send the data. And later on in this class, we're going to start programming some game server type network systems a little bit later on, but where we get to make our own protocol and decide how it works. But the idea is that's all at the application layer. Now, notice that applications that are going to rely on those lower level layers to do the work for us. But there still might be that protocol that's required for us to create, or a standard one like one of these ones up here that we need to follow to make sure things happen properly. All right, so let's look at a few layer examples here as we get to the kind of finishing up point here. All right, so at the physical layer, those are things like RS-232, which is, remember, serial cable kind of applications, V35, V34, T1, E1. And these are kind of like types of connection for broadband access. 10 base T 100 base TX, POTS, which is plain old telephone system, Sonnet DSL, 802.11a and B, G, and there are a whole bunch of variants of 802.11 out there. 1000 base TX, which was gigabit Ethernet. So these are all kind of lower level wiring kinds of things. At the data link layer, Ethernet, which these are all variants of Ethernet that we have up here, 10 base T, 100 base TX, and these are wireless Ethernet. But those are all kind of Ethernet and Wi-Fi kind of physical parts of the standard, not the data link parts of the standard. Token ring, FTDI, PPP, which is point-to-point protocol, HDLC, frame relay, TM fiber channel. So there's a whole list of possible kind of data link standards there as well. And then at the network, on the network side of things, we have IP, which is the kind of internet protocol that's responsible, like I said, for the logical addressing. There's another one that Novell used to use, Novell Networks, called IPX, which does the same thing as IP, but it's a different standard. But there's some other ones as well. ARP, ICMP still do stuff over Ethernet, but send out different kinds of messages that are slightly different packet formats than IP packets, but they're still a standard. All right, the transport layer. Parts of this, again, part of TCP is in the transport. The transport layer, remember, is responsible for segmenting and desegmenting and ensuring reliability. UDP, and then there, to go with IPX, there's this SPX networking method. Mostly now everything is TCPIP based, or UDP, which is UDP still sits on top of IP, but doesn't. Its transport mechanism is much simpler and doesn't necessarily need to do sequencing and verification of lost packets for us, which can make it faster than TCP, as we'll see when we get into the game server programming part of this class. All right, the session layer, NetBIOS, WebSockets, session establishment, and TCP. And as part of TCP is in transport, parts in session, and then the same thing for SPX. And then the presentation layer, we have a lot of different ways of kind of encoding data. ASCII versus EBCDIC. EBCDIC was a competing kind of binary representation form used by IBM machines. But secure socket layer we have in there. And then whether something's big endian or little endian, null terminated strings, or length field delimited strings like Pascal strings versus C strings, for example. Those things might be handled by a presentation layer before the data gets passed up to the end application. And there's some end applications that we put up there. Network file system, game servers, HTTP, SMTP, IMAP, FTP, all those things are examples that are at the application layer. Pretty much anything that exists as an application on the network would fall into this application space. All right, so summary. So to summarize what we talked about today is we've got this kind of layered model that sometimes you'll hear of that called a network stack. And so don't confuse the concept of a network stack for an actual stack where you push values on and pop values off. It's called a stack because it has this kind of 7-layered model where you have all 7 layers with application on top of presentation and then all the way down to the physical layer at the bottom. So it's called a network stack because those layers are kind of built on top of the lower level, on top of the lower one, on top of the lower one, all the way till we get down to the wires. So the idea is that data is communicated by being moved from the application downward through the stack on one machine. So in other words, you start at the application. It says, hey, make the function calls necessary to push data, to talk to this network, put data into it, and the data will travel down through the stack, eventually ending up on the wires. They'll travel across the wire to the other end, and then the corresponding stack on the other end, the data will pass back up through that, back to the application on the other end. So the whole purpose of that is to have this modular approach where any number of applications can use networks that have different hardware and different protocols supported for the lower layers. In other words, when I want to look at a web page, I don't care if I'm looking at it over Wi-Fi or if I'm getting it through some sort of wired connection. All I care about is I want to look at that web page. And so by having it be layered rather than all mixed together in some proprietary format, it gives us the ability to say, take this IP packet and route it over Wi-Fi right now. And then once it gets to Wi-Fi, convert it to a wire so it can go across the cable modem. The cable modem hardware talks over that kind of coaxial cable to the cable company, which then converts it back to Ethernet to talk to some router. That router then routes to some fiber. That fiber probably talks to another thing that has fiber. But notice that low-level layer is getting taken off and rebuilt for whatever kind of network it's going on. But the IP address of who we're trying to talk to, that's going to stay the same inside of it. So in other words, we're taking think of it like each layer of datagram is having its own envelope. So we have envelopes inside of envelopes inside of envelopes. And the outside one is getting opened, looked at the data inside, deciding where it's going to go, and wrapped in a new envelope over and over. Now, notice that in practice, some of the layers might be missing for certain applications or might have blurred lines between them. For example, TCP taking up 2 layers rather than one of the OSI models. But that's okay. The concept is still preserved. And I actually mentioned that at the bottom there. It says TCPIP, for example, follows this layered model, but some of the OSI layers don't perfectly match TCPIP's layering. But it's still a layered protocol suite. And it still does. It just occupies more. One TCP layer, like TCP, takes up more than one layer in the OSI model. And we'll look at more of that next time. All right, so next class, we're going to dig into TCPIP, which is kind of the protocol of the internet. And that's going to be pretty cool because what we're going to see there is how, in light of this OSI model, we're going to look at how does TCPIP kind of fit that, and what do those actual datagrams or packets of data actually look like? What is in them? How did they design it to be split up and then put back together? And how did they design it to be routed with addresses in it? And how did they design it to be then put on Ethernet that has the ability, if a packet gets corrupted because of noise, it gets repaired? And so there's this really cool thing that happens by making this layered, is that we're going to allow, that's what has allowed the internet to exist. So TCPIP is kind of the protocol that drives the internet. But that's not completely true because you still need all those low-level interfaces in order to do that. But the IP part is routing the data. The TCP part is taking it, dividing it up, and putting it back together and ensuring that if any parts get lost, they get replaced. And so to have a reliable network that connects across a large kind of area, we need both of these parts working together. And then ultimately they have to go on a physical network, so we need the Ethernet part that's at the bottom that talks to the actual hardware. So that's all for today. Everybody stay safe. I hope everybody's doing well. One quick word here at the end. I tried to go through this relatively quickly. There will be a quiz posted to the course page at some point, so I would look at that. Also, the results of my survey kind of came in, and it seems like there are some people that don't like the YouTube lecture format, but when I scored them all, it was kind of a 2-to-1 advantage for people who seem to prefer the YouTube lecture format to some online thing like Blackboard Collaborate or Zoom or something else. So I think what I'm going to do is continue with this for now, and then we'll evaluate again toward the end of the week. And at some point, just watch out. So don't just assume that you can watch these whenever. At some point, I might try a Blackboard Collaborate session as well. But that's all for today. If you have any questions, remember to post them in the comments, or feel free to ask via email, or if you're in my class, text me, phone me, send me an email, and I'll get those answered. All right, so that's it for today, but watch for that quiz later on this evening, or later this afternoon maybe, and that's it for now. So I'll see you guys next time. Ask questions if you have them, please.